Hello, Professor De Silva. This is David Sandstrom. Um, this is first project of the year, Physics 2010 R50, and the topic is the use of physics in our daily activities. I've got 8 different topics. Each topic has a clickable link, and a couple of these have more than one slide per link. Second screen here of introduction. Um, in order for us to understand what physics is in our daily lives, we must have to get an idea of what physics actually is. Merriam-Webster has a simple definition of what physics is. Physics as a science that deals with matter and energy and their interactions. It's a broad definition, but it's much more detailed than that. Physics allows us to use math and science to explain the physical way that the world works. We've got 3 gentlemen on the bottom of the screen there, 3 physicists, and the first one is Max Planck, the second one is Albert Einstein, and the third one is Michio Kaku. And they all are famous for their own right. Planck, for his quantum mechanics, he won a Nobel Prize in Physics in 1918. Of course, we know the gentleman in the middle, Albert Einstein, 1921 Nobel Prize in Physics. His most famous quotation, probably in the history of time, is E equals mc squared. It's the mass energy formula. He is known for his photoelectric effect and theoretical physics. And then Michio is known for string field theory and quantum field theory. Physics can be applied to the very simplest of things. We see in the upper left gentleman there with a hammer about to hit the alarm clock. But we know that the alarm clock will ring. It vibrates longitudinal waves through the air to his ear so he can hear. And then we see the most advanced technology of our time, which is space travel. And then we have molecular physics. It can be applied to anything. The very simple movement of motion has so many different physics characters. We have the ability to jump, rotate, push, pull objects. Next screen, just simple walking. We have a gentleman who's moving forward, and he is going in this case, a positive x direction. He's moving at a certain speed. He will cover a certain amount of distance and a certain amount of time. And as he moves quicker throughout his stride, he will be either accelerating or decelerating during that time. Moving requires friction. We have static friction in order for us to actually be moving forward. And kinetic friction is where we have 2 different objects meet, and a certain amount of friction is caused between those 2 objects. And then we have a chart there that shows the different coefficients of friction. When we're moving forward, we have in the lower part of the screen, we've got, as we move forward, we have work being done, force times distance. And in the lower part of the screen, potential energy is stored energy when we're not moving. And as we get moving, we are now exhibiting kinetic energy. And then the simple motion of falling, as we see this gentleman here trying to get up, who continuously falls. But as he's falling to the ground, his mass is moving at a velocity, and that is his momentum, creates inertia, and as that person's trying to get up, it requires work in order to do that. And in order to understand physics itself, we have to have established laws that lets us know actually what's going on during certain activities that we're doing. So as we see, just basic motion has so many different physics principles. And then we've got calculations. There's a calculation pretty much for everything here. Velocity, acceleration, distance, energy, force, momentum, um, inertia, and then of course we got the three laws of motion of Newton. I'm a respiratory therapist, and my job requires me to have so many different aspects of physics that we actually use. Most of them are gas laws, but one of the things I also do is thermodynamics, and which I'll explain. We generally go to quite a few deliveries. Most of them are anticipation of a baby not breathing well, and so one of the very first things we do when they come out, we stimulate them, number one, but we actually try to wipe off, to make them as warm as possible. We'll put a little toboggan on their head. We'll wipe them off. We'll get rid of those linens, and that's all in order to minimize the heat loss through evaporation, convection, conduction, and radiation, and those are laws of thermodynamics. And another thing I do is I do pulmonary function testing. We generally do these when we are trying to try to find out what a person's lung function is, whether they have emphysema or they've had pneumonia over a long period of time, heavy smokers, that sort of thing. We pre-qualify them before they go into surgery. And we use Boyle's Law when we do that. We place the patient in what we call a body box, and we have them breathe in and out. And Boyle's Law is just one of the laws that's used during that procedure. Another major thing we do, and it's mostly in newborns. We occasionally do it to adults, but it's very, very few, and it's done more for experimental procedures. But we give it for babies quite often, especially premature babies. We give surfactant down an endotracheal tube that I'll place, and we apply it to the right lung and the left lung. And one of the laws that covers is Laplace's law. But what it does is the surfactant actually helps decrease the surface tension in the lungs, so that the lungs, the alveoli, the little air sacs in lungs, will stay open. Another big thing that we do is use Bernoulli's principle. We give oxygen through a mask called a Venturi mask, and it uses Bernoulli's principle and the Venturi effect. We turn the oxygen up, and what it essentially does, it entrains air from the outside. Depending on how much oxygen we need, we're able to dial that in from 100% all the way down to room air, which is 21%. When we give a breathing treatment, it's the same concept. We push air through there, which breaks up the liquid into a aerosol, so we can give a breathing treatment. But what I did not realize until I started doing this is that Bernoulli's principle also shows how we have flight. It actually causes lift in a airplane's wing. Pretty interesting. I did not know about that. But so many different physical gas laws that we use that are employed, which I'm not going to go into each one of them, but just a quick listing there. Laplace's law, Boyle's law, Bernoulli's principle, Venturi effect, law of thermodynamics, van der Waals forces, Charles' law, Brownian movement, Gay-Lussac's law, Henry's law, Graham's law, Fick's law, law of continuity, and viscous shearing. Quite a few different things I do in my career field. We also, just the physics is used generally in nature. We see a rainbow. We see that light shoots through the raindrops. The white light shoots through the raindrops and refracts the light, causing the 7 different colors. The most powerful thing that I can possibly think of is lightning, but it's just the different attraction of negative and positive particles, subatomic particles, that is. And then we see hurricanes, cyclones, storms, and the different wind effects that occur in there. Then, and as we went over earlier, hearing, how we talk, and then the sound waves travel to our ear, and then how the compass always points north, because we have a north pole and a south pole that have different magnetisms, and it allows those different physical principles to occur. And then we see in our daily lives so many different aspects for productivity, communication, the way we're able to talk on a phone, how waves are transferred over, the fact that we can shoot a satellite into the space in order to talk on a cell phone, manufacturing, how we can melt steel into different products such as planes, cars, that sort of thing. Healthcare, as I talked about what I do as a respiratory therapist, but I see it in so many different aspects of healthcare. One of the things, just simple ultrasounds of our heart or of a baby through a mother's womb. It's another aspect there. And of course, we see transportation. Um, but productivity is used to every one of our lives in the things that we do. And as we can see, everything has a calculation to it. We can calculate the size of a spring that is needed when two bumper cars actually collide together so that they'll repel each other and the person will not be hurt. We see forensics now where you shoot a bullet and we can actually know by calculations where that bullet was shot from a gun. And then the many different automobile collisions that we see, and that cars are made stronger and safer, products are lighter than they ever have been, and we can have a calculation. Calculations are always given when it comes to those sort of things. And then we see our advancements in technology and our future as we go on. We see molecular physics and the dealing with subatomic particles. We have energy that from that. We see obviously the World War II's, the energy that was given from the atomic bomb. We use lasers now. We're starting to see that more than ever. And then one of the growing fields is forensic molecular mapping. It's getting to the point now where, and it's early on, that you can put your fingerprint down and only have partial of a fingerprint, and that through the molecular mapping, molecular physics, we can actually determine what the entire fingerprint looks like. So that's another thing that we're probably going to see in the next 10 or 20 years. Criminals are not going to be able to get away with what they get away with, what they normally get away with. And then the wonderful space. When we think of physics, we think of space in general, and flight and traveling to different planets and satellites, rocket ships, the way that our Earth orbits around the sun. So all those different aspects of physics we use in our daily lives. And we should get a better understanding of how and why things are the way they are by studying physics. Thank you very much, and I'm done.